Hey everybody, Isaac here, and welcome to another episode of Between Two Kets. My guest today is John Martinis. He's currently professor of physics at the University of California, Santa Barbara, but he's probably best known from his work in 2019 with Google, where they showed quantum supremacy on a 53-qubit quantum computer. That experiment and his body of work as a whole led him to win the John Stuart Bell Prize in 2021 for research on fundamental issues in quantum mechanics and their applications. So far on this podcast, I've had people on that are computationally or theoretically motivated in this field. And John is very much on the other side of things in the experimental world. My background is in condensed matter physics, mostly numerical simulations and some theory. So talking to somebody who is very much at the forefront of building quantum hardware was really fascinating, quite honestly. In this interview, we talked about the biggest problems that people face when building quantum hardware of all sorts. We also talked about the age-old dilemma of experimental and theoretical physics advancing at different paces and maybe being out of sync. And he shared some thoughts on ChatGPT, RSA encryption, and the future of quantum computing as a whole. Talking to John was really fascinating, and anybody involved in the more programming side of quantum computing or theoretical side would really benefit to listen to this entire interview. I came away from this interview thinking that I need to learn more about quantum hardware, especially our own quantum hardware at Xanadu. Building a quantum computer is super hard, and I think we need to give the experimentalists their credit for trying to tackle this seemingly impossible problem. This was a really cool conversation. Definitely watch the whole thing. Like this video if you like it. Subscribe to the channel if you want to know when more of these episodes drop. And without further ado, here is John. Welcome, John. I really appreciate your time. I know that you're probably pretty busy, so I do appreciate the hour that you're giving us here. Where are you joining us from today? The weather's great. Backyard looks awesome.
My home in Santa Barbara.
Awesome. Have you always lived in Santa Barbara?
I came to Santa Barbara in 2004. I was in Boulder, Colorado, prior to that. And then postdoc in France, and then a PhD in Berkeley, way back when, 80s.
So yeah, you've been there for a while then, and mostly in the States though, eh? Like has your education ever led you to places outside?
Well, for my postdoc, I was a year and a half in France and Paris at the CEA group with Michel Deveray and Danielle Esteve. So that was nice to go outside the country for a year and a half, but I came back.
Where did you grow up?
I grew up in San Pedro, California, which is a suburb of Los Angeles at the port of Los Angeles. So I grew up in California. I like California.
Oh, nice. Yeah, no kidding. So just outside of LA.
Just south of LA, but it's cool. It's actually in LA City, if technically, but yeah, in that area near the coast.
Yeah. What was life like growing up in LA and being I don't know if you were always into science and that sort of thing and maybe math, but yeah, what was life growing up in California like for you?
Oh, I don't know how to describe it. I like growing up in Los Angeles. It was nice. I don't think I want to go back. It's a little bit too crowded for me now, but when I was growing up, that was fine. We had, at my elementary school, they had set up a nice science kind of program near our school, which I was able to participate in. So that was nice. In high school, I went to, I think then TRW for a computer class. So there was some access. There was no computer access at my school at the time. That was a little bit before that came out. And yeah, it was a nice place to grow up.
So I've listened to some of your talks on YouTube and I can tell you're very passionate about what you do. So what sparked your interest in quantum computing? And how did you get started in the field, eventually finding yourself at UC Berkeley studying squids, and not actual squids, but the condensed matter squids,
right,
and Josephson junctions, and later on building quantum computers?
Well, there's kind of an interesting history here. Growing up, my father, graduated from high school. He was a fireman. He was always building things in the garage, various projects. So
Cool.
I grew up with that, and learned from him mostly the confidence that you can build things. Okay, so it's not surprising I went to an experimental physics. Okay, because that was kind of my background. When I took my physics course in high school for college prep, I really loved it. So that's what I wanted to do when I went to Berkeley. And I just studied physics in Berkeley. I, did well and enjoyed it. And then, went on to grad school. But at the time, both in high school, a little bit in college, my hobby was electronics. I like building electrical circuits, and I took that hobby when I started a professional career. Kind of building my own instrumentation, and a lot of times I could do experiments that no one else could do because I could build my own electronic instrumentation, and it's got me interested in John Clark's group because he was studying quantum effects on these superconducting devices. And this was some experiments that was done actually before I got there. I think that was, studied by Roger Koch and other people. So, we were looking at that. And then as I was studying these squid devices and studying their noise performance, I had gone to conferences and people were talking about these macroscopic quantum effects, and few experiments were getting done at the time. I talked to my advisor, and then Michel Devereux came, and we decided it would be nice to do experiments on these electrical devices, but seeing quantization effects in both, thinking of the currents and voltages having wave functions associated with it instead of being a classical variable. There were some ideas out there for looking at macroscopic quantum tunneling. And, we thought about it and decided that the previous experiments maybe weren't done quite as well as they could have been done. And this was an important experiment to show this. And, it's interesting because you associate quantum mechanics with microscopic entities, electrons, nuclei, et cetera. But we were saying, well, quantum mechanics can be applied to a macroscopic entity like currents and voltages, which of course many electrons floating in metal. It's more widely applicable. Now, at the time, Tony Leggett, who's a Nobel Prize winner, had said, well, maybe there's some reason it won't behave quantum mechanically. So it'd be good to test. So that was the motivation for it. And we just looked at it as a very fundamental test of quantum mechanics. We did an experiment where we measured all the parameters and checked it. We saw energy level quantization, which is a very distinct qualitative feature of quantum mechanics that doesn't have a classical analog. So I think we really, proved very conclusively that this was obeyed quantum mechanics. And of course, over the years, this turned into quantum computing as a possible way to build a quantum computer, with the advantage that if you're building an electronic device, then you can scale this up in the way that you scale up normal computing devices.
Cool. That's such an interesting story. Yeah, I mean, I've talked to a lot of people so far that have come from like a very theoretical background, and that's who I'm mostly exposed to, right? And like that's what I studied in school. Like, I was doing like condensed matter, like numerical simulations and some theory. I don't have that much like I don't talk to people that much, I guess, in like the experimental world. I mean, I work for Xanadu, so I should go up to our other floor and talk to our hardware people more. But yeah, no, this is really refreshing. So
Yeah,
like
it's an experimental world. It's a little bit different world. And what I would say in quantum computing, it's really interesting, these two worlds, because when you are in the theory world, you're abstracting a lot of the behavior. And that's what's beautiful about quantum computing, is you can abstract away and think about the concept of a qubit. And, maybe even in some of the algorithms, the qubit obeys perfectly Schrodinger equation. And, for me, what's interesting is that I'm working on how well you can abstract away, and trying to build hardware so that abstraction works better and better, as we make it better. And that's what I think is really interesting about the field. But I think a big problem is, I'm going to say with the theorists, excuse me, but the abstraction works so well that you forget there's real hardware out there, and there are real problems, and there are things that go wrong with the qubits. And, it's not a foregone conclusion that the experimentalists can solve all the problems so our abstraction is good. I mean, we are hopeful, and things are looking pretty good, but it's a lot of work to make sure that, we really obey nature, okay, in our understanding of how it's. Yeah. And that's what's great. Physics is all about understanding, how nature works, and we have to understand it very precisely when we build these qubits and quantum computers.
Yeah, so there's always that age-old like synchronization or lack thereof question between like experimental and like computational theoretical physics. Like I guess we can segue into this. The NISQ era seems to have come and gone quickly we're cresting out of it, I guess one could argue. And like I guess
there's two schools of thought here, but yes, I understand what you're saying.
Yeah. Like, where do you see this relationship between the two pillars right now, as we're getting into like I guess you can call it the ISK without the N era? Like, who's winning and who's losing? Like, what are the areas of struggle? Are we learning more new physics from experiments that we haven't predicted with theory, or vice versa?
Okay, so this is a deep question. Okay,
yeah.
So let's just start with the NISQ issue. So there's some people who think there's some interesting things we can do near term, and some people say, look, we're really not going to solve the real problems until we do error correction and build a big machine and do that.
Right.
Okay.
Right.
And I would say the quantum supremacy experiment we did at Google was great, because we showed that you could build a powerful quantum computer in the NISQ era. But it's a special purpose algorithm, and it's, I think it's clear in the last 3 years that it's kind of hard, to, go ahead and do something useful. So, there's kind of two schools of thought. That's fine. I kind of believe in both schools of thought. I mean, glad people are working on it. But the one thing that I know about both schools of thought is that all the qubits that people build right now are not good enough for NISQ, and they're not good enough for error correction. So we have to experimentally make our qubits better if we want any of this to succeed. Okay, and you can focus on one, or you can focus on NISQ, you can focus on error correction. I don't really care. All I want to see is that you're making better qubits, because to make better qubits, you can do a lot. Okay, and what happened, for example, when we were at UCSB, we got our error rates down to about 0.5% or so, 99.5% fidelity. And that was enough to do, 5 years worth of experiments, which we did at UCSB and Google. And that was great. But, you now have to get it down to 0.1% error or even lower. Okay. And, for example, right now, people are very excited about the neutral atom work coming out of Harvard, Misha Lukin's group, because they got their error rates down, to 0.5% or so. It's really good. So there's a lot of things they can do. But, okay, that's doing what we did, 10 years ago. They have a lot of stuff to do. They can scale better and do other things. That's great. But, we really have to do better. So, as I go around talking about this around the world, I say, yeah, all this is great. NISQ, error correction, whatever. We just have to make our qubits better. Everyone does.
Right.
And let's not delude ourselves. okay, by abstracting away that we have really good qubits. No, they're not good enough. And it's really hard to make qubits better.
So yeah, you touched on it there, and I want to segue to this, the QuEra work that came out about a week ago now. About 48 logical qubits from what I understand, and they didn't do error correction.
Well, why do you say logical qubits?
Well, that's what they said in their paper. So, well, there's a bit of nuance, I'm sure. But the question I wanted to ask you there
by the way, the statement of logical qubits is a little bit of a head fake. Okay. In my view, a logical qubit is 10 to the minus 10 error rates where you can do long things. But if you create a physical qubit to a logical qubit, which has more or less the same errors as the physical qubit, okay, it's logical, but how good is it? So if you're going to tell me about a logical qubit, tell me how good it is. Okay. And can you do all the operations, right? So
sorry, go ahead.
So this is a little bit, again, people are abstracting away to a concept logical qubits, but it's like, well, how good is a logical qubit?
So this is my question, I guess. The point at which, I guess, quantum computers, quote unquote, become useful, I guess, it's probably a psychological number, 1,000 logical qubits or something, which is, whatever, 1,000,000 qubits of physical qubits. So that's the industry understood number.
I started promoting that idea, quite a few years ago, so I'm not going to disagree. I wanted to throw out a number. The problem is that 1,000 logical qubits depends on what your error rate is compared to the threshold. And all the different architectures for error correction have different thresholds. So it's a rough number. It's a way for we were to talk about it at Google at the time, but it's a bit meaningless. Okay. It might take you, 10,000 or 100,000 physical qubits per logical qubit, depending on how you are with the threshold. So, but fine, at least it's a number to start arguing and then trying to figure out how to make those numbers better. Okay, so that's fine.
So my question, I guess, is like, are better qubits more important than just getting a lot of qubits to get 1,000 logical qubits?
Yes, perfect. Yeah, great question. That's the essence of my talk for the last year. Okay, right. And of course you have to scale, and that's important. But it's way more important at this point to know what your error rates are. And you can't measure your error rates on 1 and 2 qubits and know where you're at. You have to make 5 or 10. But by the time you're making 5 or 10 or 50, you kind of know that you're building a system, you know how it's going to scale. And then all I care about is the error rate. And that, I would say, error rate and then scaling goes together. Okay, but I would say now that we kind of know how to scale, error rate's a little bit more important. But you also have to talk about speed of the qubits and their architecture, their connectivity, and lots of other things. It's a system engineering problem. And it's very hard for the press to understand more than one variable. Okay, there's 100 variables to build a quantum computer. So now, now they're starting to talk about 2, which is good. Okay, but I really want them to talk about 3 or 4. But one step at a time. Okay, at least
sure.
Talk about error and qubit number, and that's big. And the reason I say, for example, speed, is that if you look at different qubit types, the speed can change by a factor of 1,000 or 10,000. And for conventional computers, 1,000 or 10,000 is enormous. And very simply put, if everything else is the same, if you have a computer that's 1,000 times faster, it's 1,000 times more profitable. Okay, if you're trying to build a business. But okay, we understand there's a lot of there's other issues, practical issues like calibration that fits into that number too.
So yeah, what are your thoughts on the various different types of hardware? I mean, it's good that we have many horses in the race here to see which one wins out. But yeah, like, what are your thoughts on, like, I guess we can still talk about QuEra here, like neutral atom quantum computers. Maybe you can give your thoughts on like photonics technology, like what Xanadu has. And I know you're a superconducting qubit guy, but yeah, like what are your
Okay,
thoughts on all the different types of
okay.
hardware out now?
So the principle is when you ask this question to someone, they always say that their technology is the best. Okay. So I could do that too because everyone else is
Sure.
doing it. Fine. Okay. And what happens is people always talk about what's really great about your technology. Okay. But this totally misses the point because what determines a technology such as CMOS, okay, is not necessarily the best qualities, but the worst qualities. Okay. And this
Right.
falls into the issues of systems engineering. When you put some really complicated thing together, you have all these constraints that are pushing against each other, and it's usually the bad one that causes you the problem to that limits what you can do. And no one wants to talk about the problems in their technology. Okay, so that's just a given. And I'm going to say also, I like to say this. I give talks on this. Is physicists are horrible systems engineers. They're born and bred to be bad systems engineers, and that's because in a physics experiment, you try to isolate all of nature around you to focus on one little aspect of the physics and really understand that well. When you're building something as complicated as a computer, you have to get everything right at the same time. Okay, so it's very easy for physicists to get in this trap, and again, to abstract away to qubits. Okay, and you forget you're
Yeah.
really living in nature. Okay, so that's the preamble. I think what's great about superconducting qubits right now is that people are building complex systems. Okay, they have pretty good error rates. We need to get them better, but the error rates are, let's say, about 0.5%. There's some isolated experiments that are better. People are building hundreds to maybe there's some announcement by IBM 1,000. No surprise. I was thinking about that when I was at Google, and you can do that. People talk about how hard it is to scale up. I have some ideas on how to do that in a way that's hard, but I think can be done. So I think they can be scaled up, and that's great. So you have ion traps, which are also doing quite well, low error rates. I think their scaling is going to be a little bit harder. They can certainly scale to one trap, or they can shuttle around, but they're a lot slower, which is actually a problem. And neutral atoms are great. They've kind of caught up to all this, and you can move them around. But again, they're even slower, I think, than the ion traps. So you have to look at the details of that. And then photonics. I don't know actually much about in the details of that, other than my understanding is you need to make very good high fidelity photon detectors, single photon detectors. So do you know what the fidelity you need in terms of measuring the error? What's the error fidelity you need for measuring a photon?
Are you asking that like you don't know the
I'm
answer?
asking you. You work for Xanadu. This is, or maybe you don't need to. I don't know.
I don't know this answer.
Okay,
I
so
can,
let me explain. This is very interesting for me. Okay,
sure.
I don't know your architecture. I know another one, and I know that that's really important for photons. But this is like the most important thing. Okay, to get that fidelity really high. And again, I don't know if that's your company, but my statement is, if it's the absolute most important thing, why don't you and everyone else in the company know about that?
So it's a great point. I think so. There's just to, I mean, give it a little bit of background about what I do specifically. Like I'm mostly working with PennyLane and like quantum
Yeah,
programmers and that
yeah,
sort of thing.
yeah, sure. So
So,
this is let me explain the point.
I got a your shirt on though, so you're properly calling me out here. I do appreciate it.
No, and it's not you, it's the whole field. And this is the way I'm thinking here. Your employment for photonics quantum computing becoming a reality, I know for other companies, I'm suspecting for you, is making really high quality photon detectors. And if they can't do that, then, it's going to go away. Now, and again, I don't know for sure that's the case in your technology, but generally you have to do something really well in qubits with high fidelity. So for superconducting qubits and other qubits, it's like, well, we have to make single qubit and 2-qubit gates with 99.9 something % fidelity. Okay, so there has to be something similar to photons for that. Okay, and again, I don't know that. And so my point is just generally in the field, it's not well appreciated how hard it is to make really good qubits so that you could abstract away your qubits. Mm-hmm. And my statement, as talking about system engineering, is if people know that that's a problem and it's talked about, then smart people will think about it and fix it, even if it's a grungy problem that, it's kind of hard to solve. But if you don't talk about it because you don't want your funding agents to know that there's something hard, because then they won't invest in you, then people tend not to work on it, and then your chance of failure goes up. So it's a system. It's very well known in system engineering that you have to solve your hard problems first, okay, and not kick them down the road, kick the can down the road. So what I'm saying about photonics, if it's true, you need high fidelity, and if you're going to guess it's greater than 99% because that's the surface code threshold. So, better than 99%. Well, how do you measure the fidelity of measuring photons that well? A friend of mine was at NIST doing this kind of thing. And, they're trying to work on those standards, but it's really hard to even measure that. Okay. And so you have to build a quantum computer until you know if your photon detectors are good enough. Okay. This is like, this is a little bit crazy. Okay. So that's a long story, but the big issue for me is the various technologies need to know what their big problem is, and they need to talk about it. Okay, because that's how you solve it. Okay, and these are hard problems to solve.
Yeah. Well, if anything, I hope that this video, when it goes out, kind of stirs up some conversation. That's all I can hope, right? Yeah.
and if there are workarounds to this, I'd love to know about it. But my assumption is there's always something hard to do, metrology wise. You have to figure out what that is, and then work to solve it. And I think that's why superconducting qubits were very successful. Is from the very beginning, people started working about the coherence, which is the big problem. Okay, and people worked on solving it in 5 different ways, and in the end, we're in pretty good shape because people figured that out.
Well, hey, I'll put some answers to some of your questions on here that I wasn't able to answer. That's the magic that I can do. I can go away and edit things, and I'm not going to chop anything up, but I'll just put the answers on the screen at least.
That's fine. Mostly what I want to do is get people thinking about what are the right questions. Yeah. And I may not, I'd love to be informed that there's certain answers to this. But that'd be great.
Yeah. Well, there's definitely all the people here that I need to query to get the proper answers. So I will do that, and I will watch this video back and send you those answers. How about
that? Great. Yeah. In the end, the system engineering question is, for your technologies, what is it, the critical thing that you have to make better and get to work better?
Yeah, the first thing that comes to mind when you said physicists are theoretical physicists are horrible systems engineers is I don't know what the whole phrase is, but there's the whole like spherical chicken.
Yes.
Thing. Like that's exactly comes to mind.
But experimentalists have a problem with this too, because again, their experiments tend to isolate nature to measure something really carefully. It's what we do. It's the basis of physics. And a good experimental design does that isolation and focus really well. Whereas when you build a quantum computer, it's much less focused.
Okay, so I don't know if you use ChatGPT at all. Do you use it for like some?
I've used it a few times. I'm actually consulting for a company that's doing large language models, so I actually know how it works. Okay.
Cool. Okay. Well, so I asked it to generate a schematic for a quantum computer based on superconducting qubits, and this is what it gave me, and I just wanted your thoughts on this. Like, is it complete garbage? I have no idea, so I figured I'd ask you because you built it.
It's kind of humorous that it gets the stack wrong. Okay, so okay. It's okay. I'm okay with that.
What's particularly wrong about it?
It's well, there's 2 qubit arrays, which doesn't make any sense, but it's basically transmon qubits, qubit array. Okay, that's the QPU, and then the dilution refrigerator, and then the control electronics, and then the quantum error correction.
I see.
And you see it's kind of jumbled it up in some way. But, for example, quantum error correction and the surface code, you need to know that architecture to know what your qubit array looks like. Okay, so, in that sense, it's kind of correct. I can see how they can get fooled. Okay, but of course, the problem with ChatGPT is that it can lie to you because it doesn't. Okay, ChatGPT, they post-program it to be very confident in its answers. Okay, so when it can lie to you really easily or mislead you very easily, but it's very confident in it, so that it gives you an answer.
What's funny is like I'll use it and I'll sometimes it is complete garbage, right? So I'll be like, no, that I'll tell it like that's wrong. I'll just say I won't give it a reason either. I'll just like that's wrong, and it'll just be like, oh no, you're right. Here's an improvement or something. Like you're right. Like it'll be very quick to be like, yeah, I am wrong, which is like so fascinating to me because like why did you give me that answer in the first place if you're so, it's just
I'm amazed that it does so well, right? But
for sure.
And it does give you the elements of it, which is good. But and the other thing, of course, ChatGPT is doing is that it's taking the average of all the information out there. And my career as a physicist has always been to challenge conventional wisdom. Is it correct? Is there another way to look at it? And I've had successes because I will challenge conventional wisdom. So, that's why I find ChatGPT particularly interesting, because in some sense it's conventional wisdom. And that often is wrong in science. In fact, in science, you're looking for conventional wisdom being wrong. That's a real advance.
Right. Have you ever used PennyLane, or like what do you use for like a quantum programming software package?
So I don't work on algorithms. I'm an experimentalist. I'm really thinking about the hardware. I try to understand what the algorithms are doing on a conceptual level and understand how the surface code works, for example, or other codes work. But I'm down here. So right now I'm thinking about individual atoms on our qubits.
I see.
That's what I'm working on right now. So I'm way far away from all of that. So unfortunately, I don't do it. I'm going to say, just in general, I'm glad people are working on all this stack and whatever and working on it. But I think once people have working quantum computers that are starting to do interesting and powerful things, then the whole stack will kind of get jumbled up and re-optimized around the hardware that you have to build. They
So
don't, and it's great that people are doing that, but it's only
yeah.
when they start connecting to real hardware that it's going to get that you're going to have the feedback necessary to make these systems really good.
So how do you think, I guess, in that vein, so how PennyLane works, or how you were to, if you were to program a quantum circuit in PennyLane, how it looks is there's just like one gate per line in a Python function. Kind of that's how it looks.
Which is good.
Yeah, I guess though, like when we're talking about millions of qubits down the line, is this how we should be interacting with quantum computers when the hardware is just, I mean, I don't want to be putting like one gate on every qubit, one line at a time. We've had these conversations internally. I'm just wondering.
That's not how you program this thing, okay?
Right.
There's a hierarchy of programming, and at some point, someone's going to be programming the gates, and the pulses, and then you build a function, and then you hierarchically build up your function. That's the way classical hardware and software works, and that's the way quantum will. And there'll be a little bit more emphasis on the low levels because there are errors and you have to do fancy things with your control. But on the end, you're going to abstract that away and build it up. And, I think it's great that people are abstracting it at a very high level right now and working on that. But I think the real difficulty is at the lowest layer where you're controlling the qubits, for the simple reason that these are not magic qubits with no errors. They have errors, and you have to work really hard on your control to make sure that they don't have any errors. So I think in the end, all the difficulty is going to be at that layer of the layer. And I'm going to say that was something that I thought was really good when I moved to Google. Is Google's a software company, and there is a lot of emphasis on people at that layer and doing the control really well, and how to layer it and how to figure out a calibration graph and whatever. And in fact, I think Google was so natural at doing that, they started not focusing on hardware like they should have, because it's, Google's a software company, but that you have to get that right. And that's right. I actually think once you get it abstracted away at that level, which is all hard, then you just build on top of it like you do with regular software, and that's straightforward. So, my whole thing is, well, how well are you doing at this kind of, I'm going to say assembly language layer, right? The very low layer.
Mm-hmm. Okay, one last fun question here, and then we'll move on to some serious ones to wrap it up. When you see movies about physics, like, I don't know, Interstellar or something like that, are you able to like turn your physics brain off and just enjoy the movie, or are you consciously verifying if like every detail is physically accurate?
So I once read about movie scripts and whatever, and if there's one thing that you have to imagine happening that's not physical, it's okay. And you're willing to disregard like one physical phenomenon. But when it starts to be 5 or 10, okay, then it starts to bother me. Okay. Yeah. So when I read that, it's like, yeah, that kind of makes sense to me. I'm willing to disregard. If you can build a whole new world about just changing one little thing, I'm okay with that. But then as soon as it gets, and of course, the problem is being a physicist, you're much more critical about what you're disregarding about nature. So that's kind of the way I look at it. So and that works pretty well. I'm trying to think of a recent movie. The recent movie, it was like that. I forget right now what the movie was, and I always joke with my family, well, okay, I can imagine that happening, but the other thing, well, no, it's so that's kind of how my own family joke, my dad jokes go.
You've talked a bit about RSA encryption and quantum breaking that. in some of your talks. And a couple of years ago, you mentioned that we should be preparing to like retire RSA encryption in like 5 years. And I'm just like, well, that's kind of almost now. And so what
Well,
is that?
and people are working on that. You know,
Okay.
there's this program on this, and people have been doing it. There are some protocols. Somehow, like building software that's reliable takes a decade. Okay, as a hardware person, it's like, you know, you're just sitting there coding, but it's hard to do all the mathematics. It's hard to make sure the coding is good, but that's coming along. They'll have a replacement for RSA before people build a big quantum computer.
And that replacement you think will be like quantum proof, I guess.
It'll be a quantum secure classical algorithm. It'll
okay.
require more resources, and you know, but you know, the internet's pretty fast, so that should be okay.
Sure.
Yeah, people are working on it. You know, I hear about this, and yeah, there's a real opportunity there. Of course, no one wants to replace all their current encryption systems, but you know, encryption systems have a lifetime. Okay, so you know, okay, we're going to have to move on to the next one. But you know, the U.S. government started really thinking seriously about this more than 10 years ago or so, and they started this NIST program, and people are working on it. I know there's companies working on it, and you know, so that's great. I mean, I think people are doing the right thing here.
My perception was that was going to be the, like, someone was going to come up, or you know, somebody was going to build a quantum computer that could break RSA encryption, and it would just come out of the blue, and then all the world's going to be looking at it like, oh no.
My statement here is that building a quantum computer is a lot harder than people think. Okay, and again, you know, the physicists who are trying to build it are you know, being very optimistic. Okay.
Spherical chickens.
Yeah, but I think in the long term, you know, there's a reasonable chance for this to happen. You know, going back to a prior statement, I think it's not the question of, you know, who's in the lead and blah, blah, blah. It's whether anyone can beat nature on this. Nature's the real competitor here. And it's really hard to do all this. You know, I'm optimistic it can happen. But, you know, it could be that you can't build it, or you can't build something big enough or good enough to do something. But I'm actually optimistic. But there's a reasonable chance it's just going to be too hard.
Yeah. I guess related to this, we're seeing a lot of oversight happening, or question about oversight, rather, in like the artificial intelligence world, whether things should be open source, stuff like that. I think it's a bit reactive rather than proactive. I mean, there's some proactivity going on there, but I think the cat's a little bit out of the bag already. But I guess, is there anything we should be doing now with building quantum computers, or thinking about how to build them, to ensure that we make good with our technology? And should there be oversight in how we advance things? Yeah. What are your thoughts there?
I live in a very you know, weird world here, because for me it's like, well, I don't even know we can build these things. Okay, it's hard, and you know, the advances are not going to be overnight. It's going to be slow. And you know, like with ChatGPT, you had what, you know, 20, 30 years of research, and then overnight it was good, right? Okay. And you know, we need more research and development with quantum before you hit that moment. But I look at this, it is a little bit different than ChatGPT and AI. I look at this more like, you know, how do you regulate supercomputers? Okay, because they certainly can do things that you want to be thoughtful about. You know, I think at this point it's more like thinking about a supercomputer than thinking about how large language models work. Okay, which is even another level of care. But it's good people are thinking about it. yeah, and I'm not an expert in this, so I can't give you any thoughts on what one should do.
Sure.
Other
But
than think about it like any other supercomputer resource.
I see. I think, I guess the thing that I'm getting at here is sometimes you can, at least with artificial intelligence, you can go down the doomsday path, full Terminator very quickly. And from what I'm understanding, the prospect of a quantum equivalent Terminator event, I guess, is like pretty low, and with
Well,
respect
okay,
to
so just to kind of normalize this, I've listened to some bloggers about ChatGPT and all these large language models. And, although they can do some amazing things, they're not very powerful, as you showed in your example, right? It was pretty amazing that they had that diagram, but also it was kind of wrong, right? And it wasn't very useful at the end. So I think people are worried that, it's pretty good right now, and then it can get even better. But I don't. I don't know. The one interesting thing that I learned, and I went to a large language model conference at Berkeley, and someone from the Bolt Law School spoke. And what they talked about with ChatGPT that was interesting was that if you generate intellectual property code or a script with these large language models, a company can't own it.
interesting.
And so you don't have intellectual property protection like you do by hiring a person and paying them and having them sign a document that hands over their intellectual property. And I think I would like to hear more discussion on this, because obviously it's a complicated issue. But obviously, if you can't own intellectual property coming out of this thing, you're going to want to hire humans to develop the intellectual property. Okay, so in some sense, humans, creators, are protected a little bit by law from this. And now, of course, how you get around it and blah, blah, blah. There's all that thing there. But, there might be some interesting things to discuss about this issue.
Cool. Well, we're about at time, so I think we'll wrap it up there. I really appreciate you coming on here again. Like, it was a fascinating conversation. You know a lot, and you know a lot about stuff that I don't know a lot about. And it was nice to like prep for this a little bit and like listen to some of your talks and kind of get an understanding of like how much into hardware you are. I think that your voice is very welcomed here, and we just don't hear enough people talk about hardware in a very open setting, kind of like this. So,
and hardware is hard. Okay, so
hardware is hard. It's in the word.
And I think that's going to pace us. But clearly there's some theory work that has to be done. But I'm mostly concerned that people can solve the hardware problem. So, and it's good to talk about that.
Well, I'll leave it at that. Thanks so much, John, for joining me here again today, and enjoy the rest of your day. It looks beautiful in California. It's a little cold and dreary here in Toronto because it's winter and it's going to get dark soon, but enjoy the sun. It was great to talk to you, and I will try and get in touch with you with some of those answers that you were questioning me about.
Great, thank you. Yeah, I would love to know.
All right, John, take care.
Thank you.
Bye now.
Bye-bye.